Hello, my name is Kirill Isakov, and I'm a doctoral student at Aalto University Nanoscience and Advanced Materials Group, which is in Finland. Today, I will tell you about an exotic but remarkably simple and effective technology with countless opportunities. I will tell you all about it in a few minutes, and if you have any further questions or interest, you can find my contact details at the end of this video. Please enjoy.
Me and my colleague, Christopher Kaupinen, have developed a process to transform atomically layer-deposited aluminum oxide into nanoporous state. We have called this film Grass-like Alumina for its structural resemblance with grass, as you can enjoy seeing at the photo here. Grass-like alumina performs as an excellent anti-reflective coating, enabling high omnidirectional and broadband transmittance. Its fabrication process is easily scalable and allows conformal coating of complex structures. First, I will refresh your memory on anti-reflective coatings. There are two main mechanisms to reduce reflection from an interface of two media. One of them is index matching. It reduces Fresnel reflection by introducing a film with a refractive index value between the index values of the two original media. The sum of the reflections at the two new interfaces, the first medium with the film and the film with the substrate, is lower than the reflection at the original surface. Fresnel reflection is minimized when the refractive index of the introduced film, NF, is a geometric mean of the two original indices, N0 and NS in the picture. Most of glasses and plastics have a refractive index of about 1.5. For interface of such material with air, index match coating should have refractive index of approximately 1.22. It is possible to further decrease reflection by carefully choosing the thickness of the film to achieve destructive interference between the two reflected waves, which you can see in the picture, the first wave and the second wave. Destructive interference occurs when these two waves have a phase difference of pi. In order to have such a situation, the film thickness should have value of wavelengths divided by 4 times refractive index of the film for normal incidence of light. To have this, a precise control over thickness of the coating is required. Destructive interference has high sensitivity to the wavelengths and incident angle of light, which is why it should be combined with index matching to achieve good anti-reflective performance of a coating. The lowest refractive index of an inorganic material is 1.38, that is magnesium fluoride. Some other dielectrics can have index as low as 1.35, and the theoretical lower limit for refractive index of a polymer is estimated to be 1.29, which are all still higher than the optimal value of 1.22. It is possible to lower refractive index of a material artificially by introducing porosity into it, but the pore size should be significantly lower than the light wavelengths in order to avoid scattering. The first step in grass-like alumina fabrication is atomic layer deposition, or ALD, of aluminum oxide. Atomic layer deposition is a thin film growth technique which involves consecutive saturated surface reactions of 2 or more precursors separated by purges of the reactor. For the growth of aluminum oxide, the precursors are 3-methyl aluminum, or TMA, and water vapor. First, a pulse of 3-methyl aluminum is introduced, which reacts with the surface of the substrate. Reaction has enough time to saturate so that aluminum methyl compounds cover the entire surface. At the same time, methyl groups react with the surface hydrogen, releasing methane. Next, reactor is purged with nitrogen to remove unreacted precursors and reaction products, thus preventing any gas phase reactions of the precursors. After that comes the water pulse. Water reacts with aluminum, creating hydroxyl groups at the surface and releasing more methane as the product. After the water reaction is saturated, the reactor is purged again. This is one full cycle of ALD growth. Atomic layer deposition is a stepwise film growth, which allows outstanding control over film thickness. Self-saturated surface reactions of ALD enable conformal growth of structures with extreme topography, as no other thin film growth technique can match. In addition, ALD is not a line-of-sight growth technique, as the precursors are delivered in vapor phase and react only with the surface. This enables batch growth of hundreds of components at a time if implemented on industrial scale. Modern advanced ALD reactors have growth speed of aluminum oxide process of up to 7 nanometers per minute, and they get better every year. For our anti-reflective coatings, we were growing 28 nanometers of aluminum oxide in Benec TFS 500 reactor at 120 degrees Celsius. It is possible to grow aluminum oxide by the same process as we have described even at 33 degrees Celsius. The process becomes slower but does not lose the main features of ALD: scalability and conformality. Deposition is at 80 degrees, which is low enough for many plastic optical components, would not significantly slow down the process. The next step in formation of Grass-like alumina is immersion of the ALD-grown aluminum oxide into heated water. Yes, as simple as that. Surface roughening of the amorphous aluminum oxide grown by ALD in water has been known for over a decade. But we have found that we can accelerate this process and use it to our advantage. In water temperatures of above 50 degrees Celsius, amorphous alumina not only roughens, but it expands as if it was a squeezed sponge and obtains nanoporous structure. This water immersion does not require any sophisticated equipment and can be scaled virtually without any limits. Required time for the transformation to finish for our anti-reflective coatings was below 30 minutes, and it inversely scales with the temperature. For films with higher thickness, we need longer processing time. For example, we have found that 30 minutes is not enough to transform a 100 nanometer thick film into nanoporous state completely. The transformation is activated at the surface and progresses into the film depths over time, which allows some play with the processing time to achieve an interface of S-grown and porous film. However, we did not use this feature in our anti-reflective coatings. This is a scanning electron microscope, or SEM, image of grass-like alumina. The water treatment does not etch the film, but it expands the alumina by dismantling the S-grown film into flakes of fibers that are still connected to the substrate, lifting them up. Partial delamination occurs. In such a way, the film becomes porous, with the size of the features below 100 nanometers. As you can see, the film indeed has a grass-like structure. We attribute the creation of such specific topography in part to the effect of water surface tension. When the water dries off the samples, it brings the dismantled film pieces together, like here, creating close to conical structures, though very chaotic. The transformation increases the film thickness, as you can see in the SEM image. The porous film is about 200 nanometers thick, while we have deposited only 28 nanometers of ALD alumina. It is clear from the film structure that there is a refractive index gradient, as there is more alumina at the bottom and more air at the top. It is very beneficial to know the gradient, but direct measurements are very challenging. We have used simple transfer matrix method to fit the refractive index profile to the measured transmittance. As you can see, we have a good fit, and the update index profile is physically reasonable, as it approaches the value of 1.6 at the bottom, while the S-grown aluminum oxide has a refractive index of 1.64. This also correlates with the fact that ALD-grown aluminum oxide has good adhesion to various glass types as well as to most polymer substrate. Gradient refractive index enables smooth transmission of light because there is no sharp refractive index contrast, which cause Fresnel reflection. Gradient anti-reflective coatings have great broadband and omnidirectional performance. Unfortunately, creating a gradient refractive index profile usually is a challenging task and requires sophisticated techniques, though the obtained performances, for example, multi-layered glancing angle deposited coatings, are excellent. Grass-like alumina fabrication, in contrast, is not a complicated process, as you just saw, and does not require a multi-layered deposition. The refractive index gradient forms there naturally. We have studied different water temperatures for the grass-like alumina formation and achieved average transmittance of 99.3% in the visible range of spectrum for double-side coated glass. The peak transmittance was 99.5%, around 540 nanometers. We have targeted these wavelengths to have the maximum transmittance by our choice of film thickness. This proves availability of high control over the optical properties of the fabricated coating. Grass-like alumina outperforms most published anti-reflective coatings on glass. It has performance comparable to the best multi-layered glancing angle deposited films or multi-layered spin-casted polymers. Simplicity of fabrication and massive scalability with this kind of broadband transmittance are unprecedented. Additional experiments have confirmed that it is possible to tune the peak transmittance to near ultraviolet range for grass-like alumina deposited on quartz. Our coating also has impressive omnidirectional performance. As you can see, even at 60 degrees incident angle, the coated glass has better transmittance than bare glass at normal incidence. At 80 degrees, the enhancement in transmittance to bare glass is almost 14%. Such omnidirectional transmittance is highly desirable in many applications, including imaging systems and detectors. The transmittance spectrums keeps a flat shape up to 50 degrees angle of incidence. The spectrum has almost negligible shape degradation at 60 degrees. And even at 80 degrees incidence, the color reproduction does not experience strong distortions. To our knowledge, grass-like alumina has the best omnidirectional transmittance within single-layer coatings. Here you can see the difference in transmittance between uncoated glass on the left and the double-side coated glass on the right. The coated glass is slightly difficult to notice, while the bare glass adds a little of gray color to the transmitted image. The difference is even more apparent at high incident angles. Mostly, distortions caused by refraction give away the coated glass. At the same time, bare glass has a stronger gray color and reflects glare from lamps. It is vivid from this photo that coated glass is almost invisible. You can only notice the edges of the glass piece. This also demonstrates that there is no scattering of the transmitted light with grass-like alumina. A little more details about the grass-like alumina formation. The graph presents you results of ellipsometrical measurements performed on grass-like alumina formed at different water temperatures. Ellipsometry is an optical method to measure effective refractive index of a film and a corresponding thickness. We used single wavelengths or laser ellipsometry. As you saw from the electron microscope images, the real thickness of the film is about 200 nanometers, but the used ellipsometer cannot process a gradient refractive index. It understands the grass-like alumina as a solid film with one constant refractive index, hence the difference in the film thickness estimation. As I mentioned before, we used 28 nanometers of ALD alumina, an immersion time of 30 minutes for all these samples. Ellipsometry shows an important thing here. We not only have a gradient refractive index, but also the effective or average refractive index of our film is around 1.2, which is very close to index match value for glass, which is 1.22. In addition, ellipsometry has helped us to choose the film thickness for accurate positioning of the transmittance peak at a desired wavelength. Thus, even though ellipsometry does not measure the real thickness and refractive index for grass-like alumina, it is still a useful measurement technique as the effective values provide quality control. With the specified immersion time, the process activates at water temperatures above 50 degrees. But there is very little dependence on the film properties after this temperature. Another big advantage of this water treatment is that the transformation saturates at a certain state. After the water has worked its way through the film, further time spent in water has negligible effect on the film structure. The saturation in respect to temperature and time simplifies implementation of this technique even further. In additional experiments, we have also confirmed grass-like alumina formation from the film's atomic layer deposited at 80 degrees Celsius, which makes it applicable for many plastical substrates. As I have mentioned, atomic layer deposition enables conformal coating of substrates with extreme topography. Here, you see surface of black silicon coated with grass-like alumina. Not only alumina deposition has smoothly covered all the sharp peaks and the deepest trenches, but the transformation to nanoporous state also did not distort its conformality. It is vivid that grass-like alumina anti-reflective coating inherits outstanding conformality from atomic layer deposition. No other anti-reflective fabrication methods have comparable ability. So basically, it's the only game in town. Grass-like alumina applications do not end with anti-reflective coatings. It can be advantageous to utilize this extremely high surface area and deposit other functional materials on top. Here you see a nitride and an oxide films deposited by atomic layer deposition on top of grass-like alumina, on top of black silicon for ultimately high surface area. This can be used in sensors, emitters, absorbers, and other devices. This work would not have been executed without strong support from various organizations and people. Specifically, I would like to thank Doctor of Science Alexander Peres for his insights and expertise in atomic layer deposition, and Professors Harri Lipsanen and Markus Sopanen for their support and guidance. This project would not have become a reality without them. Please do contact us for research collaboration or licensing of this technology. patent of this technique is pending. I will also be happy to answer any of your questions regarding Grass-like Alumina and beyond. Do not hesitate to ask them by email. If you have ideas how to use Grass-like Alumina for other applications and want to bring them to life together, contact us. My email is kirill.isakov@aalto.fi. You can see more data and information about Grass-like Alumina from our recently published article at ACS Applied Materials and Interfaces. I hope I was able to spark your interest with this technology.